Welcome back to this course on combinatorics. In the last week's lecture, we took a very short survey of the notions related to partially ordered sets, and we hope to use it this week. So what we are going to do today is to look at a technique called Mobius inversion. So this gives us inversion formulas that can be used as we did in the case of inclusion, exclusion, other topics. So to recall, we said that a partially ordered set is locally finite if all its intervals are finite. Now let us look at the set of all intervals of a poset x and denoted by int of x. Now consider the set of all functions from int of x to some field, let's say k. So this set is denoted by I of x comma k, and together with the algebra that comes from the field, the K-algebra, this is called the incidence algebra of the partially ordered set x over the field k. Now, we don't really need these details, but just to make it complete, I will just mention it. So that this I of xk is a vector space over k, where the convolution is defined by, or the product is defined by the formula fg of x comma y is equal to summation over all z that is between x and y, f of xz, g of zy. Now this summation is well defined because we assume that x is locally finite, which means that the set of all such z is going to be finite, so the sum is finite. So therefore, this product is well defined. Now, equivalently, we can also, instead of looking at this incidence algebra, we can just look at the set of all functions f of x for our purpose. And the set of all functions f of x, which takes x cross x to r, such that f of x comma y, f g of x comma y, it again for two functions, f and g, the convolution is defined by summation of x less than or equal to z less than or equal to y, f of xz into g of zy, such that so whenever x is less than or equal to y and 0 otherwise. So we are just adding 0 here, for the other functions where this interval is not. So therefore, they are not comparable. We don't have the interval. So for all those elements, we are defining it to be 0. So yeah, so these two are essentially the same. Now, if you look at this, you can show that the convolution, the way we have defined convolution, it is associative. So I want you to do this as a homework. So prove that f dot g dot h or f dot within bracket g dot h is equal to f dot g dot h. That proves the associativity for f1, fg, and h in our f of x or in int of x. Now again, without mentioning it, I just assumed the field here to be R. We can assume it to be C also, or in fact any field. But for our purposes, it will be sufficient to assume it is either R or C. Now, I define another function delta that says that delta of x comma y is equal to 1 if x is equal to y, and it's equal to 0 if x is not equal to y. Okay? This is also defined over the poset. And this function delta acts as an identity for the convolution. So that is a claim. So again, you can prove that by using the definition of convolution. F dot delta is equal to delta dot f is equal to f itself. So therefore, it proves that delta function is the identity function. Okay. Now, here is a proposition. Take any function in f of x. So then the proposition says that the following statements are all equivalent. So first is that f has a left inverse. Second statement says that f has a right inverse. Third statement says that f has a two-sided inverse. And finally, we say that f of x comma x is non-zero for every x in the poset x. So all these statements are equivalent. So that is the proposition. So how do you prove this? Well, let us look at the first one of the cases. Let's say f has a right inverse called g. Now, if f has a right inverse g, then that means that the convolution product fg is delta, right? By the definition of right inverse, and this is true if and only if. So when is fg is equal to delta, which means that fg of x comma x is equal to delta of x comma x, which is 1 by the definition. Delta of x comma x is equal to 1. So therefore, f of xx into g of xx is equal to 1 for every x in x. Then g of x comma y is equal to negative summation x less than z less than or equal to y, f of xz into g of zy divided by f of x comma x for every x strictly less than y in x. Now, why is this true? So we are saying that fg is equal to delta if and only if this is the case. So, or g is a right inverse if and only if this is the case. Now, why is this? Well, just look at the definition of the convolution product. So if you look at the convolution product, we have fg is defined to be summation. What is that? Fg is summation overall x less than or equal to z less than or equal to y, right? Fg of x comma y. G of f of x comma x times g of f of x comma z, f x comma z times g of z comma y, right? Now this is f of fg of x comma y. So by definition of the convolution product. So if you have fg of x comma y, fg is delta, right? That is the assumption. Fg is delta. Now if fg is delta, then fg of x comma y is equal to delta of x comma y. But delta of x comma y is equal to 0 if x is different from y, and therefore if x is different from y, this is equal to 0, right? Equal to 0, x not equal to y, right? So in the summation, right, the first term is f of x comma x, right? When z is equal to x, then g of x comma y, right? So you take that sum, that keep that term on the left side and move everything to the right. So what is the remaining thing? That is summation x less than z less than or equal to y, f of xz into g of zy. So this is what you will have on the right side, right, with the minus sign. Now So on the left side we had f of xx into g of xy, right? So you take that to the right side, you will get g of xy to be this way. So therefore, if g is an inverse of f, right? Then g should be defined. So if it should be defined, then f of xx cannot be 0. I mean, f of xx is not 0 because f of xx into g of x is equal to 1, right? And therefore, we can do this division, and therefore we get g of xy this way. So therefore, if there is a right inverse, then we already know that f of xx is different from 0, and g of xy is in this form. Okay, so similarly, you can show the other properties, right? If f has a left inverse, then also similar idea works. And then using the associativity property, we can also show that it has a two-sided inverse. Okay? So all these are identical to the assumption that f of xs is different from 0, because in that case we can of course define g this way. And so I want you to do all this computation as a homework, not computation. Formally writing this as a homework. So complete the proof by showing the existence of left inverse, and then using the associative law that these inverses coincide. The left inverse and right inverse coincide. Now we define one more function. So we already defined delta function. So we are going to define another function, zeta function. So the zeta function of a poset is defined as follows: zeta of x comma y is equal to 1 whenever x is less than or equal to y. Zeta of xy is equal to 1 whenever x is less than or equal to y, and it is 0 otherwise. Now this zeta function contains a lot of information about the poset. We will maybe use it sometime, but at the moment I want you to look at this and then try to observe some properties about it. And here are a couple of properties that you can try to prove. The first is to show that if you have the zeta function, then zeta square of x comma y is basically the cardinality of the interval x, so the closed interval xy. So this should be quite easy to prove. Then you can also prove that zeta minus 1 whole raised to t of x comma y counts the number of chains of length t from x to y. So look at these two functions, zeta square and zeta minus 1, and then look at the properties and then show that these properties are indeed the case. So this is a homework. Now one observation is that the zeta function must have an inverse, right? Because by the earlier property where we proved that if the function f of xx is different from 0, right, then it is invertible. So here we have defined zeta of xx is because x is comparable to itself, right? Zeta of xx is equal to 1, so therefore it is different from 0, and therefore the function has an inverse. Now we define the inverse of zeta function and call it to be mu. Okay. So by the definition of inverse, zeta mu of x comma y is equal to mu zeta of x comma y, which is equal to delta of x comma y. So delta is the identity. Now we call mu the Mobius function. Okay? So the inverse of zeta function is called Mobius function, and we can see that mu of x comma y is actually equal to 1 if x is equal to y, and it's equal to minus summation x less than or equal to z strictly less than y, mu of x comma z if x is less than y. Now why is this? So if you look at the definition of you know the inverse here, right? So inverse was looking something like this, right? G of xy is equal to minus summation f of xz g of zy by f of xx. Right? Now, similarly, using that definition, we can try to see why this should be the case for the mu, right? The Mobius function. So how do you prove this? So to prove this, well, we can just look at the definition of the the convolution product, right? And the fact that mu is the inverse of zeta, right? So what is mu zeta of xy is delta of xy, right? So let us look at what is mu zeta of xy, right? So mu zeta of xy is summation overall by the definition x less than or equal to z less than or equal to y, mu of x comma z into zeta, right? Zeta of z comma y, right? Which is equal to delta of xy, right? No, and this is whenever x is less than or equal to y. Now, zeta function so has a nice property, right? Zeta function is equal to 1 when x is less than or equal to y, and 0 otherwise, right? So in this interval, what we know is that zeta function is 1 whenever it is looking at the value z, because z is between and y, it's in the interval. So therefore we know that this summation can be written as by us, because zeta is 1 whenever we are counting, and otherwise it is 0. So therefore this is actually equal to summation x less than or equal to y, x less than or equal to z less than or equal to y, right? Mu of x comma z, that is equal to delta of x comma y. This is true. Now if x is equal to y, then what we get is that, like, there is only one term, so mu of x comma x is equal to 1. Now otherwise, because it is delta of x comma x, right? Otherwise delta of xy is equal to 0. Otherwise delta is equal to 0. Now if delta is equal to 0, we can move one of the terms to the left side, right? For example, mu of xy we move to the left, so therefore we will get this identity, because we just took the last term, right, mu of xy from here, and therefore that's because the summation is 0, we get mu of x comma y is equal to minus summation. So that is the proof that this is indeed the inverse of zeta of xy. So we have the Mobius function, which is the inverse of zeta. So let us look at some example and try to compute one or two cases of the Mobius functions. How to compute Mobius function? So let us look at the simplest example possible. Like, consider the chain. Let us say the set of integers 1 to n ordered by the usual less than or equal to order. Right? So usual order over the natural numbers. So this is our poset represented. The chain is represented like this. Now what is this we already know already, but we can just write it. So theta of x comma y is equal to 1 if x is not equal to y and 0 otherwise, and delta of xy is equal to 1 if x equal to y and otherwise 0. Now, by a definition of the convolution, right, and the definition that zeta and mu are inverses of each other, zeta mu of x comma y is equal to delta of xy. Now, mu of x comma x is equal to 1, right? We already established that it is actually 1, right? And mu of xy has this formula summation minus x less than or equal to z less than y mu of x comma z. So let us try to use this and try to compute mu in this case. So what is mu of x comma x? That is 1, we already know, right? So let us look at what is the next, right? Mu of x comma x plus 1, the next element. Now this by the summation here, it is minus summation mu of x comma x plus 1. No, mu of x comma x, because the last term is x plus 1, which is a strict inequality, therefore we don't consider that. So because we have already taken it to the left side, so therefore mu of x comma x plus 1 is equal to minus of this, which is minus 1. Now what is mu of x comma x plus 2? Well, that is minus of, first is mu of x comma x, which is 1, then the second term is this, which is minus 1, and then that's it. So this is minus of 1 minus 1, which is 0. And if you continue this, you can see that this, because this sum is 0, this dissolves, and you will get all the subsequent entries to be also 0. So therefore we can see that mu of I comma j is 1 if I is equal to j, is equal to minus 1 if I is equal to j minus 1, or I plus 1 is equal to j, and 0 otherwise. Okay, so we computed the Mobius function of the chain. One more example. Let us look at the poset Bn, which is the poset of all the subsets of an n-element set ordered by the inclusion. So consider a subset of b subset of xn, right? So two sets A and B, such that A is subset of B. Okay, this is also important. Now our claim is that mu of AB is equal to minus 1 power cardinality of B minus cardinality of A. Okay. So we want to find out mu, but we just start with this claim. Now how can I start with a claim before finding it out? Well, one way to do this is to start from the smallest and then try to work out a couple of examples, right? Very small examples, and then try to see a pattern, and then you can conjecture it. So that is something you should try. Maybe take this without looking at this expression that is given. Try to come up with this prediction by looking at some example. So one can do that, and suppose we have done that and we have the prediction. So now how do you prove this, right? Mu of AB is equal to minus 1 raised to cardinality B minus cardinality B. Now we can use induction here. So for the base case, we have mu of A comma A is equal to 1, right, by definition, but that is equal to minus 1 raised to 0, right? Cardinality of A minus cardinality of A is 0. So therefore the base case satisfies the induction hypothesis. Now suppose B is different from A, right? If B is different from A, then we have some elements in B minus A, right? Because B is containing A, right? So look at cardinality of B minus A and call that to be small p. Now because of again the containment, we know that this is also equal to cardinality of B minus cardinality of A. Now let us apply the induction hypothesis. So mu of a comma b is equal to, by the by the previous definition that we have, right? It is minus summation overall y. I think it should be y, such that a less than or equal to y less than I mean a containing y containing b, where this is a strict containment, mu of a comma y. Okay, so I should make it more clean. Okay, that is of y. Now, so now what is this? Well, here because the size has become smaller, we can use the induction hypothesis. So therefore, this is equal to minus summation a containing subset equal to y, strict subset b, minus 1 raised to cardinality of y minus a, right? Because y is already strictly smaller. So now what is this? So this is equal to, now if you look at, we are looking at the subsets, right? Y, and you can, instead of counting over this y, we can also count over the, with respect to the cardinality, right? So what is the cardinality of y? Well, if you look at the cardinality of y to be, let's say, k, then there is exactly p choose k, where p is the the largest cardinality here, right? P choose k elements y, right, with cardinality k. I mean, P choose k sets y with cardinality k, and therefore the contribution will be minus 1 raised to so okay, sorry. So what I wanted to say was that k is basically the cardinality of y minus a. So yeah, so y minus a ranging from 0 to p minus 1, you see that there is precisely p choose k of them, and so therefore minus 1 raised to cardinality of y minus a is k, p choose k, where k is ranging from 0 to p minus 1, k ranging from 0 to p minus 1, will be precisely this sum. And what is that? Now this sum, you can verify that this sum is precisely the binomial expansion of 1 minus 1 whole raised to p, except the last term, right, with a minus sign. Therefore this is precisely minus 1 raised to p choose p, and that is minus 1 raised to cardinality of b minus a, because p is the cardinality of b minus a. So that is it. So we have showed that by induction this holds. Okay, so mu of a comma b is equal to minus 1 raised to cardinality b minus cardinality of a for the Bernoulli poset Bn.